So remember, covalent bond means shared electrons, but do they share equally? When two electrons are shared between an atom, the electrons are pulled in a tug of war between the atom's nuclei. Remember, those negative electrons are attracted to the positive protons in the nuclei of both atoms in the bond. In equal sharing, like a diatomic molecule, the bond that results is called a nonpolar covalent bond. So for example, O2 is a diatomic molecule. Let's do the math and draw O2 structurally. So each atom in a diatomic oxygen wants 8, so 8 times 2 is 16. But oxygen has 6 valence electrons, and in the molecule there's 2 of them, so 6 times 2 is 12. Wants minus has is 4, and 4 divided by 2 is 2. So we need to draw 2 bonds between both oxygens. That means we need a double bond. The last thing we need to do is check our octet and make sure the oxygen has 8, and it doesn't. Each bond represents 2 electrons, so each oxygen here is sharing 4. So we need to draw 4 electrons on each oxygen like this. So that's oxygen, and in the tug of war between both oxygens, they both have an equal pulling power. Now that pulling power that we're talking about is what we learned about in chapter 6, that thing called electronegativity. The scale of electronegativities was invented by this man, Linus Pauling. He was the one of the only two-time Nobel Prize winners. He actually won one for chemistry, and he won a Nobel Peace Prize for his anti-war activism. He's a very interesting guy. I encourage you to read more about him on his Wikipedia. And he looked up electronegativity, determined electronegativity values, and made a scale. And this is a scale of electronegativities. And if you look at these numbers, we can see a trend. And the trend is the electronegativities get higher as we go up and to the right. Now we learned about this in chapter 6. Electronegativities are higher as we go to the right because we have more positive protons pulling those negative electrons in tighter and closer. And as we go up, we have less shells, which means we also have less shielding. So the protons in the middle have more of an influence on other electrons in a covalent bond. And remember, you don't need to memorize these numbers because they're all on table S. But it would help to know the trend, but remember you could always look up the values on table S if you were unsure. So what if the sharing is not equal, like in something that's not a diatomic molecule, like HCl, hydrochloric acid? So no need to do the math here. I know there's only one bond that can be formed between an H, so I know it's a single bond, H and then Cl. We still need to check the octets though. Hydrogen wants 2 and it has 2. Chlorine wants 8 and it only has 2. So to make chlorine happy, we need to draw in 6 unshared electrons on the chlorine. Okay, now when we need to determine the polarity, we can go to table S and look up the electronegativities. If you find hydrogen, you'll see that it's 2.1. And if you look up chlorine, you'll see that it's 3. So in the tug of war for electrons, chlorine is stronger. It's further to the right. It has more protons and more pulling power. So when the electrons are being shared between hydrogen and chlorine, they're not being shared equally. They're spending more time around chlorine than they are around hydrogen. So this makes the bond polar. So the chlorine is going to acquire a slight negative charge because the electrons that are shared in this bond here are spending more time around the chlorine, and those electrons, remember, are negative, than they are around the hydrogen. Okay, so as they spend more time over here, this side is going to acquire a slight negative charge. And because the hydrogen is losing one of its electrons for a portion of the time, it's going to acquire a slight positive charge. And those charges, those slight charges, look like this. So it's actually a lowercase delta. Uppercase delta is kind of like a triangle. Lowercase delta is like a lowercase d with a funny little tail on the top. And it denotes a partial charge. It's much less than a true 1 plus or 1 minus in an ionic bond, but it's a partial charge. Another way that you can show the electronegativity differences is with a type of arrow. In this is what I will typically use more in class and in these notes rather than these partial charges, just because it's easier to draw. And the arrow looks like this. So it's an arrow, but the positive side, the partially positive side, gets a little hash mark. You need to remember the arrow is always pointing to the more electronegative atom, which in this case is the chlorine. So how polar is a polar bond? It turns out there's different degrees of polarity. So the greater the electronegativity difference, or END, the more polar a bond is. So this is a chart that I want you to just copy down in your notes. Unfortunately, you have to memorize this. It's kind of nitpicky, but I've seen it show up on the Regents a couple of times. So just to be sure, I want you to memorize some of these ranges and what they mean. So if you have an electronegativity difference between 0 and zero point 0.4, the bond type is nonpolar. And a good example of this would be any diatomic molecule. Whatever hydrogen's electronegativity, that number subtracted from itself is going to be 0. If you have electronegativity of 0 or something really small like 0.4, you can just consider the bond nonpolar. If it's between 0.4 and 1, it's moderately polar. An example would be HCl. Between 1 and 2, it's very polar. That'd be something like HF, hydrogen fluoride. And anything greater than 2, it's an ionic bond. And you should know it's an ionic bond before you even do the electronegativity difference, because an ionic bond always features a metal like sodium, something from the left-hand side of the table, and a non-metal like chlorine, something from the right-hand side of the table. All of our other examples here are two nonmetals. So a polar bond tends to make the entire molecule polar because you have an area of difference. This side of the molecule is slightly negative and this side of the molecule is slightly positive. So in other words, we have poles. We have a negative pole and a positive pole. So HCl has polar bonds, therefore it is a polar molecule. So a molecule that has two poles, a negative pole and a positive pole, is called a dipole. The effect of polar bonds on the polarity of the entire molecule sometimes also depends on the molecule's shape. So just because you have polar bonds doesn't mean you necessarily have a polar molecule. Let me show you an example. Carbon dioxide. Now we've drawn this before, but let's do the math again. Each atom in the molecule wants 8 valence electrons to be happy, and I have 3 atoms in this molecule, so 8 times 3 is 24. Now let's figure out how many valence electrons this molecule has. Carbon has 4, and I have 1 carbon in this molecule. Oxygen has 6 because it's in group 16, and I have 2 oxygens in this molecule, so 6 times 2 is 12. So we'll do wants minus all the has, 24 minus 4 minus 12, and that will be 8. And then we need to divide that number by 2 because a covalent bond is a sharing of 2 electrons. So if I divide that number by 2, I'll get 4 bonds. So I need to connect these 3 atoms with 4 bonds. We need to decide which is the central atom, and of course it's carbon because it's the most metallic. So carbon's in the middle, and I need to attach an oxygen to it. I always start with single bonds, and then another oxygen on the carbon because it's the central atom. And I have 2 more bonds I need to put in to make this molecule happy. So I need to have double bonds here. The last thing I need to do is check the octets. Carbon in the middle is happy. It wants 8. It has 8. Oxygen wants 8, and currently they both only have 4. So I need to draw in 4 unshared electrons like so. So when I draw my lines of polarity, I need to do it for every bond. So there's 2 bonds between this carbon and this oxygen. So in the tug of war for electrons between this carbon and this oxygen is winning. It has a higher electronegativity, which is why the arrow is pointing to the oxygen. Okay, I don't need to draw it for the other bond. It would be going the same way, so there's no reason to draw another arrow here. But I do need to do it for the bond between this carbon and this oxygen, and of course it's going to go the same way. Oxygen is still more electronegative than that carbon, so it's going to be pointing away. So this molecule is considered nonpolar. Despite the fact that these bonds are polar, the molecule is nonpolar, and we say it's nonpolar due to symmetry. This is a symmetrical molecule in terms of poles. On this side I have a negative pole, and on this side I have a negative pole. Remember, to have a polar molecule I need a positive pole and a negative pole, and I don't have a positive end. All my positive is kind of locked up in the middle on this carbon here. So again, this one is nonpolar due to symmetry. So let's look at another one, H2O. So we've seen this before as well. Oxygen has 6 valence electrons because it's in group 16, and I have a spot on the corner here where I can bond with a hydrogen, and another spot here where I can bond with the other hydrogen in the formula. So here comes one, and there's the other hydrogen. So in the tug of war for electrons here, I need to do it for each bond between this hydrogen and this oxygen. Oxygen is more electronegative. Oh, we'll do the bottom one first. So this oxygen is more electronegative, so the arrow is going to go towards the oxygen, and the same for over here. So this molecule is polar. Now, it might look like it's symmetrical as you learn about symmetry in art class. You could, think, well, I could fold this down. It's the same on this half as this half if I put a little imaginary line here. But you remember, we're always looking for poles. Does it have a negative end? And it does. The oxygen end that's sticking out here is more electronegative. So here's my negative pole, and then here's my positive pole. These hydrogens are not as electronegative, so we have a slight positive charge on this side. No matter which way we turn this molecule, I'm always going to have a negative end and a positive end. So this is polar. So remember, when electrons are shared in a covalent bond, they are not always shared equally. In the tug of war for electrons, the more electronegative atom will always win. And the differences in electronegativities always make the bond polar. And you can show this polarity with symbols, those lowercase delta signs, or arrows. Molecules with areas that have different electronegativities than others are polar molecules. If you have one end that's slightly negative and one end that's slightly positive, it's always going to be a polar molecule. But not all molecules with polar bonds are polar molecules. Sometimes they become nonpolar due to symmetry. So you want to look for lines of polarity, those little arrows that are canceling each other out, like in our carbon dioxide example. If they all point out or they all point in, that's a symmetrical molecule and it will always be nonpolar. That's it for this video. If you have any questions, please let me know.